Hello and welcome to this tutorial. I will show you how to use compute shaders in Godot 4 to store environment data and textures and use those in shaders for visual effects. Now this may sound like a very niche topic, but this is actually a very broadly applicable topic. And so I'll show you by showing my 3 demo scenes that are all on GitHub and you can view yourself. So the first demo scene is this painter that fades over time. As you can see, it's in real time and it uses a compute shader to track my mouse position. This is what we're going to be making today. This demo, which actually is almost the same code. I just changed a very few things. And as you can see, I created an interactive snow environment for my character to walk in. And the snow fades back over time, but also disappears around the character. And the last demo I have for you guys is this shoot demo. Walk around and my bullets will leave bullet holes on the mesh where they hit them, and they will be stored there for eternity, so I can save the texture that is created because of this and use it again and again. So let's get started. I'm using a new Godot project for this, and because we're going to do 2D painting part only, I'll create a 2D scene. Let's call it world, and we're gonna go with a sprite. So this is actually all we're gonna need, and let's attach a script. Let's create a ready function. So the big difference between a compute shader and a technique I showed last time is that a compute shader has a lot of overhead and boilerplate code we're going to be needing to get it ready. A compute shader needs something called a rendering server to run. The rendering server is a very low level API, even lower than the node system, that allows us to directly communicate with the GPU. There are two options you have when working with a rendering server. You can either create a local rendering device, or you can use rendering server but get rendering device. So the main difference is that this is like a fake server that is very useful if you only do calculations on your rendering server. But today we're also going to be needing our textures, and since our textures need to be rendered to actually become textures, we can only use our main rendering device. Now this comes with another limitation, that is that you actually want to execute all the GPU codes that needs to run in the main rendering thread in the main rendering thread. So we cannot use a default rendering function. We're going to make our own ready function, and I will just call it render ready, just to indicate that this is our ready function within the render thread. Well, how do we execute this on the render thread? It's very simple. We do rendering server dot call on render thread, and then you just can pass your callable. So this way we make sure that everything we do on our ready setup is executed correctly. Let's actually mark this to make sure that all the code below is only executed on the rendering thread. This keeps it easy. While our rendering server gets a rendering device over here, so we need to store that. I'll just call it var rd, and it's a rendering device. So I'll say rd is rendering certificate rendering device. For the next part, we need two more variables. We need a shader file, and we need a shader. I will call this an RID, and I'll tell you what it is in a second. First, a shader file is load. I'm just gonna go with res example.plsl, and then we can use a shader is rd shader create from spurf, and then we can use save file get spurf. We use our RD, so that means that we are doing this on our main rendering device, hence we do it on a rendering thread. And what is returned is an RID. An RID is not actually a shader, it's just an opaque pointer to where the shader is. This means that once this is done, this code, we're not out of the scope for the shader. We only have scope for the RID of the shader, which means that Godot can't free the memory. So we need to do it ourselves. So on exit 3, we are going to call rd.free RID, and we're gonna free our shader, and in the end we're gonna set our RID free. This is very important. Always make sure that every RID, so that's everything you make on your rendering server, that it gets freed before your application is closed. Otherwise, you will get memory leaks. So next, we're going to need two more uniforms, two more variables. One is a uniform set, which is also going to be an RID. And we're going to need a pipeline. And you guessed it, it's an RID. So our uniform set is a way of giving a lot of variables to the shader once. So we're going to need it. First, we need to initialize it. So we're going to say uniform set is RD uniform set create. And right now we don't have any uniforms, so it doesn't really matter. We can pass our shader and we can set the set. I will explain what the set is in a moment. Next, we need the pipeline is rd.random pipeline create shader. Before we do anything else, let's make sure that we free our memory. So I'm going to free my uniform set and I'm going to free my pipeline. So a very strange thing about Godot right now is that it will give you an error on this line. I don't know why. Even the docs say to free your uniform sets, it would make sense. But when you try to, it will give you an error. So I'll comment it out. This is everything we need to set up to get our rendering server ready. Now we can actually start with rendering, with calculating. So we're going to need a process function. You don't need to run your compute shader every frame. You could run it once if that's what you want. You could also run it like independent of the frames, but on another way. But for the painting, I'm just going to use it every frame because that's easy, because I can just use the process function. Once again, we cannot use the actual process function. So I will call a function called render process. It will go over here, of course. Let's actually pass in the delta. In order to run our compute shader, we need a compute list. So we're gonna call compute list is then we need our compute list to bind to the pipeline. So we're just gonna go compute list. We can pass and compute pipeline we already made. RD compute list, and then somewhere it should be uniform set. Yes. Once again, we're gonna use a 0 over here, same as in here. So we need to, this is the point where we actually set our uniforms in the shader. Compute list dispatch. Compute list, because it's the list we want to dispatch. And then tells us asks us how many groups you want to dispatch. Compute shaders work on a GPU, and a GPU doesn't run one single thread at a time. The GPU runs as many threads parallel as possible. In the shader, you will define how many threads of GPUs you run. And then here you define the amount of work groups. Every work group has as many threads as we define on the GPU. If I give it like 4 work groups here, and I can send the GPU, each work group has 12 threads, that means that in total 48 times the code is executed. The next work group will only start when the first work group is finished. There's a bit of a funny thing here where we don't actually only have one direction, so you cannot say I want 4 work groups. You can say I want 2 work groups in the X direction, 2 work groups in the Y direction. I'm just gonna go with 64 by 64, and you even get a set direction. I'll give him 1. If you didn't understand what I just tried to explain, Godot docs are pretty good in explaining this as well. Maybe it's better if someone wrote it down for you. Okay. With that done, actually our compute shader is almost done with running. We just call compute list end, and this is it. So now our compute shader runs. I cannot execute the code, of course, because this is a problem and this is still a problem. So first, let's start by making a shader, because then we know what we need to do for the uniforms. For a shader, you don't get to make GLSL in Godot yet, but right now you need your own IDE. You can use Notepad or you can use anything else. I will use VS Code for this. I made a file called example.glsl. In case you are not familiar with VS Code or you never code outside of Godot, Notepad works just fine. It's just you don't get the highlighting. So let's get started. The first thing we need to do is tell Godot that we're computing. We do this by saying #compute at the top of our script. Actually, execute is, of course, you say it like this. We also need to define our version of GLSL. For Godot, you will always save it going version 450. Okay, this is where we get when it gets a bit tricky. So this is where you define the amount of threads you want to use. Okay, so in an ideal world, you would just say here the amount of threads you actually need. But since your GPU has limited space, we need to divide it up in work groups. So this is the amount of threads you run. And then you can just say how many in the X direction, Y direction, and Z direction you need. Since I'm going to be using a 512 by 512 image for this tutorial, I will use an 8. If we want our code to execute, we need to give it a main function. Our main function is just what executes upon running. We want to have the mouse position, store it in a place in the texture. So that means that we need to get our mouse position. How do we do that? Again, start by saying layout. We can give the binding of 0. Mouse position is going to be a buffer. And every buffer, you don't need to find by name on the GPU, you find it by binding location. So by just saying the binding 0, you know this is the first buffer we need. It's the texture we're going to give a binding of 1, meaning that you will find it by just saying, hey, I want the first uniform. Then we can say set. I'm going to set it to 0. So this set corresponds with, in Godot, this 0, right? We also need to make sure that we use the right type. So we're just going to say our standard memory type for 30, uniform restrict read only. Actually, I'm not using uniform, I'm sorry. Restrict read only buffer. I'm gonna do it like this, mouse position. So I use a couple of keywords. Like buffer is very simple, it's just an amount of memory. Read only is also simple. We're not gonna change in this shader our mouse position. We use this to tell the GPU, hey, this memory is completely safe. You don't need to worry about it, that we are gonna change it in this thread while the same thread is trying to access it. So this optimizes already. Restrict means that we're not gonna use pointers or something. So we're not gonna try to access this memory from anywhere else than the variables for the memory. Like GPUs give you a lot of ways to access the memory. We have an X things and we're gonna got mouse position. So this is how you define a buffer in your shader. So that means that here we can give ourselves a mouse position. I'll call it impulse, and it's gonna be an I-vec2 of our X and Y. Since these are ints, I'm using this to protect the data type. We're also already going to be able to define a UV. So this may sound very strange to you, that are used to how most things do this. But I'm gonna use an integer factor too. So that means that these are whole numbers. A global invocation ID just tells us which thread it is we're executing. So you think I need to divide this some way to like get a 0 to 1 value, but in compute shaders you actually can change how you sample your texture. And you can also sample with the UV like this, and divides are pretty heavy for a GPU, so you want to use them as little as possible. And this is one way to do that. Then we're gonna check if the difference between our UV and our mouse position is less than some arbitrary constant. So we can just say we're gonna make a function. It's gonna be our distance squared. So we're gonna first create distance between the two. Then it's just a very simple distance function. As most people know that are advanced enough to do compute shaders, you don't want to use the square root operation too many times. And this is just one way by working with distance squared instead of the standard distance function that GLSL does have. We can just optimize our code a bit. I'm just going to say if distance squared and we can pass in 2 for vectors. So I'm going to pass in my UV and my mouse position. If the distance between those two is less than some arbitrary, so I'm just going to say 20 times 20. So if it's what the actual code is going to be, if the distance is less than 20, we need to store to our image. Well, this leads to one more thing. How do we get our image? It's surprisingly similar to this, just a couple of differences. So it's once again a layout. This time we're going to be binding to 1. The set is still 0 because we want to set those at the same time. Then we can call this actually a uniform restrict because we're not going to do anything funny with it. It's an image 2D and it's a texture. I'm just going to call it texture. So for the format of the image, since we're only using like 1 bit, I'm just going to use the red channel. But yeah, if you want to store more information in your texture, you can of course add the other bits as well, like the blue channel, the green channel. But we only store like distance to mouse position, so that just goes in 1 channel. And we can store it by using image store. First it wants our texture, then it wants our UV, and then it wants the value we have to store. I'm just going to do it like this. So I want like to store a vector 4 only consisting of 1.0. This may sound strange because I just said we only use 1 channel, and now I'm going to store a vector 4 there. So we're not actually storing the vector 4, it's just that GLSL will convert your vector 4 to whatever format you've set over here. So you don't need to worry about like making sure this and this match. You will always use a vector 4 over here, and this will define how the memory is actually saved. So this very simple compute shader is enough. This will run and will do the trick for us. So we can save it and go back to GODOT. As you can see, I apparently made a mistake in my shader because this means that it didn't compile correctly. This should be accessed like this and not just how I did it before. And let's open a GODOT, and you saw it just compile real quickly over there. So our shader should be good to run. So before we can run it, as you saw, we made 2 buffers that we need to set. We made a texture and we set a mouse position. This is where our uniform set is going to come in, and we're going to go back to the render ready function. So first, the mouse position. The first thing we need to do is we're going to need to create a buffer. So we can create a storage buffer. We need a size and we need data before this. So let's create a very simple buffer. I will call it, actually, let's call this buffer. And since we're making something on the rendering server, we need to store it so we can get rid of it later. Okay, let's make a very simple buffer. So we just need 2 values. So we are gonna use a packed int 32 array, and this int array will just use 0, 0 for it. Now our buffer can only exist in bytes array, so we need to convert this to a byte array. Here we needed a size, so we can just say very simply dot size, and then we need our data, and that's just going to be our end buffer. So now we created our buffer, but we can't actually set it yet because in here we can only set uniforms. So we need to create a uniform. So we can say buffer uniform is rd uniform.new. We need to set the uniform type. As you can see, there are a lot of types we can store, but we just want a storage buffer. Then we can set what the binding position is. So this is a 0. So this means that, like you can see the binding over here, this is gonna match to our binding over here. So we're setting it to the correct place. Then we need to add this buffer to this buffer uniform by add ID, and we can set our buffer over here. So now we have our buffer with the mouse position ready. We can put it in here. Now we need to make the image buffer. I'm going to create the texture uniform a bit backwards so it's more logical. For the texture uniform, we can just first make this. And we can of course say texture uniform is rd uniform dot new. Then we say texture uniform dot type, and it's a uniform type image. We can set the binding because this is going to be 1 since this is 1. Okay, now we need to add our ID. And our ID is going to be our v text. Well, we don't have a v text yet. Let's get the error away. V text our ID. Let's free it already, just to be sure to save it on memory. V text. So that's a very simple function called rd.texture create. We need a format for here. We need a texture view rd. So it's called the rd texture view. We could just give it a new one. We don't really need to change it. And we need to pass some data again. The image is going to be easy. Let's actually do it like this. Create empty. So I'm going to use a 52 by 50, 12. We're not going to use mip maps. For the format, I'm going to see if I can find it real quick. This one. So this means that we're only using the red channel and we're using the full float, which is, as you can see, we're using a full float over here. Okay, so for the data, we can say image.get data. Okay, that's one of the 3 resolved. Now we need the format. And let's do that over here. RD texture format new. Okay, format. The format just describes our image for the GPU. And it's gonna involve like just setting a lot of stupid variables like width. We need to set the height. We need to set the format. So this needs to match with our image format. And as you can recall, we only used the red channel. We used a full bit and it's a float. And we're almost done, except we need to tell the GPU what we're gonna do with this. So we have the usage bits we need to set. For those of you that don't know how bits work, it's really easy. You can just add them together and Godot will know what to do with it. For this project, we need all these bits. Sorry, I copied them from another file. Line all of them. Having done all that, we actually have our format ready and we should be able to parse it. Now running this will do absolutely nothing. Well, it will do a lot. It will just update the texture continuously, but we don't display our texture anywhere and it stays on the GPU currently. So we are not finished because what are we going to see? So it's very easy to actually make sure that we can see this. Texture to the RD. So this is a pretty new type that came with Godot 4.2, I believe, and is really useful because there's 2 ways we could get our data, right? We could get it back from the GPU, make it an image out of the bytes that we get, and set that to the sprite routine. This would suck because it means that the whole idea of like using our texture information on the GPU is destroyed because we would constantly have to sync our clocks between the GPU and CPU and wait for the data to be passed around. It can be used quite good. It's actually kind of similar to the approach we used before in the other video, but it's more so if you are assuming something that's not going to be updated every frame. So what the texture to the RD does, it's really simple. It just holds an RID, which is just, as we remember, a pointer, and it will just tell the sprite where the memory on the GPU is, since the rendering of the sprite is going to happen on the GPU anyway. and our texture is already on the GPU. So there's no need to get it to our computer first. With the texture to the RD, we can just say, hey, it's on the GPU already. Please just use that. And we won't have to render the texture twice. This texture to the RD is also why we're working on a rendering thread, because it means that our texture has to be rendered before we can use it. So that's a lot of information. How do we use it? It's really simple. Texture RD is texture to the RD dot new texture RD texture RD RRD, a lot of RDs, is our vtext. So we set our RRD pointer to our virtual texture that we created on our shader, and then we just say sprite.texture is texture RD. So this finishes it, and if I run the scene, you can see that there's errors. Let's fix those first. Before we can run this, we need to add texture uniform. And as you can see, nothing happens. Well, something does happen. Our compute shader runs every frame on this, but we don't actually pass the mouse data to it, and we only see a quarter of the image. So let's change that by going into here, over here, and we can just add a camera so we can actually see everything. And then we need to go back here, and we need to, in process, we need to somehow update our buffer. Well, this is really easy because there's this function called update buffer. So first we need to make a buffer. We can just say get global mouse position, and then we add half of 512. Okay, so why does this work? Well, because the mouse position is already in pixels. So if I am on like minus 256, this would be 0, 0 for our compute shader. If I am on 256, it would be 512 on our compute shader. So by just 256, 256, I'm calling this our mouse pulse. How we're going to do that is rd.buffer update. We need to set our buffer. Before we do this, we need to give an offset is 0 because we don't want to start in the middle of our buffer, just from the beginning. We will create an end buffer again. So use it like this, and we will give it end buffer. Well, this is really simple. We did it before. End buffer is backed in 32 array, mpost.x, mpost.y, 2-byte array. Okay, let's execute this. And there you have it. It paints. This works. Yeah, so now you can paint with your mouse in 2D. Amazing. So this may seem like not really that useful. So this may seem not very useful, but what you need to remember, this is just a very simple example where we use our environment data, in this case just the mouse, which is also part of the environment in your game, and we use it for a visual effect in game. The real carrier of this is the texture to the RD, because it's able to speed up our process so much. Like if I implement this in 3D, which is kind of what this snow demo is, it's the same as my previous video, which is in compute shaders. It's so much faster, and it comes because of the texture to the RD. This way, you can just create so many visual effects, and it's used in so many games by just getting a texture on the GPU and storing there your data. Like you can even store flower positions and stuff like that in there, and you can use it to create interactive shaders. So I can show you a bit of what I changed in each demo, but it's not that much. So for this one, actually, the most that I changed, so the big difference is that I just fade the color over time. So I first load the image and then I fade the color over time. You need to then do some logic on which color you're gonna store, but that's everything. Like that's all the difference that I did, and you can make like your color disappear. Amazing. I use the exact same compute shader for this. This snow demo uses the same compute shader as the one we almost made today. So it's really easy of just storing data, and you can, of course, now we're just storing 2 ints. You can store like how many ints you want in your picture at one time. And it will be really, really fast every time. And you need to remember this is an amazingly big image. It's 512. You don't need that much data most of the time. There are, however, cases when this is not the ideal solution. I didn't make the last video just to like say it's completely useless. Like that same approach can be used in different instances. Do not use it for painting. Like it's horrendous for performance. But like bullets, it really depends on the game you're making if it's worth it to do bullet holes on your GPU. Because the main advantage you have on your GPU is that it's so much faster if you execute it every frame. But the main drawback is you have to execute more code on your GPU, and your GPU just has a limited number of threads. And if you use so many compute shader that you're going to use all of your threads, you will have to choose which effects to layer, and layering your effects means it will be slower again. And how often is someone going to shoot into a wall? Like if you're making FPS, yes, someone is going to shoot in the wall like hundreds of times in a minute. Do it on your GPU. If you're doing something like this, where it's just someone can have a gun and they can shoot at walls, you can always opt to do this on your CPU only, because it's not worth it to create the overhead, and it's not worth the drawback of having to execute GPU calls instead of just doing this on your CPU. I hope you guys found this useful. The demos, as I said, up on GitHub, linked in the description, and I wish you a very pleasant day.